Okay, in section 2.2, we're talking about basic differentiation rules. It's what you've been waiting for. You no longer have to find the derivative using the limit process, which I know was loads of fun. There are much quicker ways, most of the time much quicker ways to find the derivative of a function to help you find the slope of a tangent line. So anyway, objectives. First of all, we'll talk about the rules, the basic differentiation rules. Some of those are the constant rule. We have the power rule. And I think this is the one that a lot of you last time started to notice as we were finding the derivative using the limit process. You started to recognize some patterns. We're going to talk about the constant multiple rule. And some difference rule. You talk about derivative of sine and cosine. We're going to see another application of derivative in addition to finding the slope of a tangent line. We're going to talk about rates of change. Seems like a lot to get through, but these rules, most of them are pretty basic. Okay. So we'll start with the constant rule. Okay. This one says the derivative of a constant function is 0. So if C is a real number, and f of x equals C, then f prime of x, or the derivative of f, is equal to 0. So pretty easy one to remember if you're taking the derivative of a constant, then it equals 0. For example, we are finding the derivative, so y equals 7, then you would say derivative of y, or dy dx, that's one of the notations, one of the different notations for derivative, would equal 0. Or if we had another notation, function notation, if we had f of x is equal to 3, you would say f prime of x is equal to 0. Okay, so you just need to be familiar with the different notations here of derivatives. Well, pretty easy examples there. Let's move on to the power rule. A little more widely used. So if n is a rational number function f of x equals x raised to the power of the n is differentiable and the derivative with respect to x of x to the n is equal to n times n to the x minus 1. And I think this was the pattern that some of you recognized when we talked about section 2.1. For example, if we had to find the derivative of, let's say, x to the third using the limit process, you would have found that the derivative is 3x squared. So if we were finding the derivative with respect to x of x to the third, you notice that the exponent drops down to the front as a multiplier, and then you decrease the exponent by 1. That's what this little formula here is saying. X to the power of n, the derivative, you drop the exponent down to the front, and then you reduce the power by 1. Okay. So just it's not really a special case, but quite often students get confused with this one particular instance of the power rule, so it is helpful to kind of write it on its own. The derivative with respect to x of x is equal to 1. It's just an application of the power rule. The exponent of 1 drops down in front, and then you're left with x to the 0 power. So let me write this out here. 1 times x to the 0 power, but then x to the 0 power is just 1. So you're left with 1. Just something that's helpful to remember. So for example 2, a couple here to try. If you're going to find the derivative of f of x equals x to the 6th, for part B, g of x is the cube root of x. And for part C, y equals 1 divided by x squared. So, first one's pretty straightforward. When the exponents are integers, those seem to be the most, or the easier problems for students to do. You just follow the power rule explicitly. You drop the exponent down in front. So f prime of x is the derivative with respect to x of x to the 6th. You don't need to write all this out. I mean, f prime you need to write out, but this, I'm just writing down all the steps here. Using the power rule, the exponent drops down to the front as a multiplier, and you decrease the exponent by 1. And quite often, actually most of the time with radicals, it's more useful to rewrite into exponential or rational exponents. So if we think about g of x as x to the power of 1/3, now we consider g prime of x. You move the exponent to the front as a multiplier, and then you got to decrease the exponent by 1. Now 1/3 minus 1, so you have 1/3 minus 1, but 1 is 3/3. It's a 3 right here. So 1/3 minus 3/3 is negative 2/3. And now you're going to have to rewrite this a little bit. You don't want to have a negative exponent. So we'd finish this off as y, or g prime of x is 1/3 times x to the power of 2/3. And the power rule, can apply here as well, but again we need to rewrite this, so we think of y instead of 1 over x squared is x to the negative 2. Now you can apply the power rule, this basic power rule here. So we're going to say that y prime is negative 2 times x. Now you decrease the power by 1 to negative 3. Okay. And then you don't want to have negative exponents again, so this is negative 2 over x to the third. So some pretty basic examples of the power rule. We're going to be seeing a lot more of this on this assignment and the next assignment. So next topic was called the constant multiple rule. Really all it boils down to is the case where, let's say some of these examples had coefficients in front. How do you deal with that? This is what the constant multiple rule addresses. So if the function f is differentiable, and c is a real number, then c times f is differentiable so the derivative with respect to x of the product c times f of x is equal to c times f prime of x. So essentially what this says is you still find the derivative of f and you multiply it with that constant c. So the constant c really has no effect on the derivative. It multiplies the original function and it multiplies their derivative function as well. So for example, for part A, if we're going to find the derivative of a few functions here, let's say that y is equal to 2 over x. For part B, let's consider the function f of t is equal to 4 times t squared over 5. For part C, let's say that y is equal to 2 times the square root of x. For part D, y equals 1 divided by 2 times the cube root of x squared. And then for part E, y equals negative 3x over 2. Okay, so coming back up here. For part A, again, it's going to be helpful to rewrite y so that x is in the numerator and not in the denominator. So we think of this as y equals 2 times x to the negative 1. And if we now take the derivative with respect to x of 2 times x to the negative 1, according to this constant multiple rule, we can take this constant 2 outside of the derivative function here and just find the derivative of x to the negative 1. So this is 2 times the derivative with respect to x of x to the negative 1 so the derivative of x to the negative 1 is negative x to the negative 2. Now you multiply with that constant 2, and we're going to get negative 2 over x squared. Now for part B, maybe not as necessary, but I'm going to rewrite this slightly. F of t can be thought of as 4/5 times t squared, because you don't want to confuse this constant 4 as just the multiplier. It's really 4/5 as the multiplier. So when we're considering the derivative, f prime of t, we can take 4/5 out as a constant multiple, and then find the derivative with respect to t. So now it's derivative, so it's d over dt, that means the derivative with respect to t of just t squared. So then that's 4/5, and then the derivative of t squared is 2t, so that equals 8t over 5, or 8/5 t. Now, on part C again, with radicals, you're most often going to rewrite them using rational exponents. So y prime is going to be 2 as the constant multiple. Now we're going to multiply that by the derivative with respect to x of x to the 1/2. So this is 2 times 1/2 x, and then you have to decrease the exponent. The exponent was 1/2 originally. If you decrease that by 1, you're going to get negative 1/2. Now when you multiply, 2 times 1/2 is 1. So it's 1 over the square root of x, or x to the 1/2 if you want to leave it with rational exponents. Okay, now on part D, before we do the derivative, let's rewrite this a little bit here. This is going to be 1/2 times x to the negative 2/3. Okay, so now when we find y prime, we can consider 1/2 as a constant multiple, so we can leave it out, and now we're going to find the derivative with respect to x of x to the negative 2/3. So this equals 1/2. Now the derivative is going to be negative 2/3 x, and if you subtract 1 from 2/3, you're going to get negative 5/3 as an exponent. Okay. 1/2 times negative 2/3 is negative 2 over 6, which is negative 1/3. So this is negative 1 over 3. Now you can't have negative exponents, so this has to hop down to the bottom. X to the 5/3 as an exponent. And on part E, again, a lot of students get confused and think that negative 3 is the coefficient of x, when it's really, if you want to consider this written a different way, it's negative 3/2 times x. So when we find y prime, we consider negative 3/2 as a constant multiple, and we just find the derivative with respect to x of x. And if you remember, I think I wrote it down up here somewhere, the derivative of x, the derivative with respect to x of x is just equal to 1. So coming back here, this derivative turns out to be 1, and then 1 times negative 3/2 is negative 3/2. Let's get into before we get into the next rules, the sum and difference rules, as you get more comfortable with this, quite often the power rule and the constant multiple rule are really thought to be combined as one rule. Maybe as the last example here, part F, if we're doing y equals 3x squared, the derivative, or y prime, you're going to drop this exponent down in front, and it's going to multiply that constant. So you're going to get a 6 times x. So you really don't necessarily need to write the constant multiple separate from the derivative, and then because you're going to end up multiplying that constant anyway, and you'll get a lot more practice with this. So anyway, the next objective here we go. We're going to be the sum difference rule. So basically what this says is the derivative with respect to x of the sum of two functions is equal to the sum of their derivatives. Okay. The same thing is true of the difference, so if you're taking the derivative with respect to x of the difference of two functions, and that's equal to the difference of the derivatives. You're most often going to see this rule applied to polynomials. For example, for part A, if we had the function f of x equals x to the third minus 4x plus 5, then the derivative f prime. So really what we're looking at here it is one function. F of x is one function, but you can consider each term to be its own function. So when we're taking the derivative of this entire function, you can now consider each individual term to be, in essence, its own function, and you can apply this sum and difference rule to this. So rather than thinking about taking the derivative of the entire function, take the individual derivatives of each term. So we're going to have a 2x as the derivative from this first term. From the second term, the derivative of negative 4 times x. Remember, x has an exponent of 1. The 1 is going to drop down. I multiply with the negative 4. But then that's going to leave you with x to the 0, which is just 1. So the derivative of this term is negative 4. And then we have the plus 5. And if you remember right from the beginning, the very first thing we talked about, the derivative of a constant is 0. Well, I mean, there is a plus 0 there, which you don't need to have. So the derivative of that polynomial, oh, I just changed the exponent here, didn't I? That should be an x to the third. Oh man, alright. Let's back the truck up here. So the derivative, if it's x to the third, like it should have been, is 3x squared. There we go. And then the derivative of this middle term is negative 4. And again, the derivative of that constant is just 0. Okay. And again, there's another polynomial here. Let's do g of t is negative t to the 4 over 2 plus 3t to the third minus 2t. So the derivative, g prime of t, it is the derivative with respect to t of the entire original function. Make sure I write it correctly this time. But again, since it's the sum or difference of individual terms, you can just take the derivative of each individual term as if it were its own function. So the derivative of this first term is negative 4t to the third over 2. the derivative of this middle term, if the 3 moves to the front and multiplies the 3 that's already there, you're going to get 9t, and then you decrease the exponent by 1. And then this last term here is negative 2. The derivative of that last term is negative 2. Again, because this t has an exponent of 1, the 1 drops down and multiplies with a negative 2, making negative 2. And then if you decrease the exponent by 1, you get t to the 0 power, which is just 1. So it's negative 2 times 1, which is negative 2. And that's most often how you're going to see the sum or difference rule applied to mostly polynomials like this. Now you're going to want to look through and simplify this. Negative 4 over 2 can be simplified to negative 2. T to the third plus 9t squared minus 2. Now we do have to do a little bit of trigonometry, and this is just very, very basic. The trig derivatives are going to get slightly more complicated, but just because we're talking about basic differentiation rules, let's talk about sine, cosine, so the derivative with respect to x of sine of x is equal to the cosine of x. And then the derivative with respect to x of the cosine of x is equal to negative sine of x. And what you can expect of your homework, again, are just very, very basic derivatives. Nothing too complicated just yet for trigonometry, at least. So, for example, if y is equal to 2 sine of x, then y prime, you can consider this 2 as a constant multiple, so it has no effect on the derivative. Really what we're trying to find is the derivative of the sine function here, which is just cosine. So y prime is equal to 2 times the cosine of x. Or here if we had y equals cosine of x over 2. Not 100% necessary, but you may want to think about rewriting y here as 1/2 cosine of x. And again, this 1/2 is just a constant multiplier out in front. So take the derivative of the cosine function, which is negative sine. So then y prime is negative 1/2 times the sine of x. So the end part of this lesson is rates of change. So again, it's another application of the derivative. We've used it in the last section to find the slope of a tangent line. It can also be described to, or used to describe rates of change. And more specifically, it's how one variable changes with respect to another. You may have already seen this. I'm actually guaranteed you've already seen it. If you've taken physics, you've seen this as you've studied position function versus velocity function versus an acceleration function. It's a study of how position changes relative to time, or how the velocity changes relative to time. That's what it means, how one variable changes with respect to another. So some of the things you might run into in this textbook are population growth rates, water flow rates. We're going to study a lot of velocity and acceleration that you've seen in your physics classes. So just again, to keep it basic, in this section at least, one of the more common uses for rates of change and derivative are used to describe an object moving in a straight line, and more commonly a falling object, which obviously moves in a straight line. So Let's talk about rates of change with a falling object. So the function s that gives the position relative to the origin of an object as a function of time and that time variable is usually called t, so as a function of time t is called the position function. Now, one thing you might remember was discussed very, very briefly back in pre-calc was called an average rate of change. It would have been very, very early on. Essentially all it was finding the slope between 2 points on a graph. That was called the average rate of change. So the average rate of change, if we're talking about the position formula or the position function, would be called an average velocity. So as position of an object changes, that's because of the velocity. If an object moves, then it has a velocity. So if we track the object's velocity over time, we can talk about what's called the average velocity. And it's the change in distance, or s, change in position really, divided by the change in time. So just to go back to last year in your pre-calc class, you might recall this. If not, it's not a huge deal, but if we had some function f of x equals x to the third minus x, and you were supposed to find the average rate of change between two x values, x1 equals 4, x2 equals 8. All that essentially boiled down to was the slope fx2 minus fx1 over x2 minus x1. That's essentially what's happening here with the average velocity. So for example, if a ball is dropped from 100 feet its height at time t is given by this position function. S of t is equal to negative 16 t squared plus 100. So if you were to find the average velocity between time equals 1 second and time equals 2 seconds, that's essentially what you would have done last year in a pre-calculus course when you're finding the average rate of change between 2 points on a graph. It's nothing more than the slope formula. It's the change in the position divided by the change in time. So the change of position is going to be s of t2 minus s of t1 divided by t2 minus t1. So we have to figure out the position at 2 seconds. We have to figure out the position at 1 second. So the position after 2 seconds is negative 16 times 2 squared. 2 squared is 4. 4 times negative 16 is negative 64. Negative 64 plus 100 is 36 feet. Position 1 second, S of 1 is negative 16 times 1 squared is negative 16. Negative 16 plus 100 is 84. So what we have here is 36 minus 84 over 2 minus 1. This is negative 48 by 1. So the average velocity, or the average rate of change, is negative 48 feet per second. Now, just to be clear here, the velocity is negative. What that means is traveling towards the origin. If the velocity were positive, it would be traveling away from the origin, which makes sense in this case because the ball is falling down towards the ground. So with respect to an observer on the ground, the ball is moving towards that observer. If the ball were traveling upward, it would be moving away from the observer, so it would have a positive velocity. Now, you don't want to get this confused with speed. An object's speed is the absolute value of its velocity, so speed can never be negative, but velocities can be positive or negative depending on the movement of the object toward an observer or away from an observer. Anyway, that's the average velocity. But if we wanted to find what's called the instantaneous velocity at a specific moment of time, then that would be the limit of this as the change in time approaches 0. Well, this is just that limit process that we talked about in section 2.1. This is nothing more than the derivative. So all of these basic rules we just talked about apply here. We don't have to use this limit process to find the velocity. So the velocity v at time t is s prime of t. So let's use a similar scenario. We've got a falling object. So the position of a falling object under the influence of gravity. This is neglecting air resistance, is given by this position function. S of t is equal to negative 16. Well, actually, let's do this in general. This negative 16 is the gravity on Earth, but in general, it's 1/2 g t squared plus v sub naught, or v sub 0 times t. V sub 0 is the initial velocity. G is the effect on gravity, and on Earth it's negative 32 feet per second. But it could change depending on, I guess, what planet we're talking about. S sub 0 is the initial position, or the initial height of the object that's falling. So, last example here. Let's say at time 0, a diver jumps from a platform 32 feet high, into water, obviously. The position is given by this position function, S of t, and it looks like we're diving on Earth. That's good. It's negative 16t squared plus 16t, so this means he jumped with the initial velocity of 16 feet per second, and plus 32 because his initial height was 32 feet. Now you do have to pay attention in these position functions to the initial velocity. It's positive 16, which means he jumped up first before he started to travel downward, which makes sense, most divers do. So part A is when does the diver hit the water, and part B is what is the diver's velocity at impact. Well, when does the diver hit the water? The word when means that we're going to be finding a value of t. T is time. So when the diver hits the water, the diver's height or position is 0. So what we're doing here for part A is solving the equation 0, because that's the position. Negative 16t squared plus 16t plus 32. So if we factor out a negative 16, and then factor, it's going to be t minus 2 and t plus 1. So we get two values of time, 2 seconds and negative 1 second. Now it doesn't make sense for time to be negative, so the only value of time that makes sense considering the domain restriction of this problem is time equals 2 seconds. So it takes the diver 2 seconds to hit the water. So for part B, we need to figure out how fast this diver is traveling at impact. So we knew the position function, S of t is equal to negative 16t squared plus 16t plus 32. Speed or velocity is the derivative of the position function. So velocity is equal to the derivative of the position function. And we can apply the power rule here with the sum and difference rules that we talked about. So it's going to be negative 32t plus 16. Now, this, much like we talked about last time, the derivative, if we were talking about section 2.1, the derivative is a function that helped you find the slope of a tangent line. Here, this derivative velocity is a function that can help you find an instantaneous velocity, but only at a particular value of time, so you have to know that value of time. And in this case, it's 2 seconds. So the velocity at 2 seconds would be negative 32 times 2 plus 16. So it's negative 64 plus 16, which is negative 48 feet per second. So when the diver hits the water, he's traveling 48 feet per second. It's negative because he's traveling towards the water. His speed would be described as 48 feet per second, but his velocity is negative 48 feet per second. And that's pretty much it for section 2.2.